Hi guys, welcome to my YouTube channel, and in today's video we will be discussing about the internal architecture of Kafka, right? And we will do a deep dive into it. We will understand the important concepts and the components involved in as part of the Kafka architecture, and then we will try to see how it helps in today's world, right? So let's quickly begin with it. So you might already know that Apache Kafka is an open source messaging platform. So when I say open source messaging platform, that means, so there are two forms of communication, right, between services. One is sync, another one is async. So let's say there is service 1 and then there is service 2. Service 1 is wants to call let's say some feature of service 2, but service 2 is kind of slow and the feature it wants to process takes some time. Let's say it takes 10 minutes of time to process it, right? So if you call it synchronously by API, then service 2 has to wait for 10 minutes, right? Which is not the correct way of doing so. So what we will do, we'll basically do a throttling in between. We will introduce a messaging platform, a queue kind of, and then service 1 will send a message to service 2. Service 2 will consume it whenever it is ready, process it. Right after 10 minutes, it will send the response back to service 1, right? So this is where these kind of scenarios are the situations where you basically use the messaging platforms, right? But the important facts about Kafka is that it delivers the performance, it's very scalable, it's very durable, and it's always available. These are the main important features of Kafka, right? So if somebody asks you the question that why one should prefer using Kafka over other platforms, then the answer should be it has high performance, it is very high scalable, it is very durable, and it's always available, right? So before doing a deep dive into Kafka, let's understand what is event log. And why event log? Because Kafka is something that works on event log, right? So event log is very, very easy. Assume that you have a log file, right? And then every time you want to write something, you are writing in the end of that particular log file, right? So, and then let's say if you are writing, if you already have 5 lines, then where will you write the 6th line? You will write the line, you will write the 6th line after the line 5th, right? So this is kind of an event log. Now I'll come to that point why event log we discussed, right? It's very, very simple, that because of Kafka implementation of event log, right? So this is, I have shown that message 1, message 2, message 3, message 4, this is kind of a mistypo. So this is message 5, right? So now let's understand the most important concept of topic, right? So the concept of topics. So topic is a place, let's say, as I said, that there will be a queue, right? And the same way you will have a topic. So for example, you have a service 1 here, right? And then you have a service 2 here. Now assume that your service 1 is your producer and then this is your consumer, right? Now there has to be some medium, then you introduce a queue in between. So this producer will send to this particular queue, and then this consumer will basically consume from that particular queue, right? Now what is that? A data structure, implementation of that data structure where your messages will be stored in a broker, right? So this, assume that this particular queue is your data structure, right? When I say data structure, that means how you will store your data in memory. Then this is your broker. So let's say this is your Kafka. We will understand what is broker, just hold on for some time. And then inside broker, what is that will hold your message? What is that data structure? So you say that, okay, it's a queue data structure. Okay, then specifically, what is that implementation of queue? So I'll say a topic. How topic will work? The way topic will work is, let's say you will have that queue, right? And then when you will send a message, so I'll send that message, let's say here, right? Then you want to send the next message, I'll send it, let's say M1 here. You want to send the next message, I'll say M2, I'll say M3, I'll say M4, right? M0, right? So all those new messages will be keep on pushing in the end. So let's say this is your end and then this is your start, right? So now consumer will sit here when you push that particular message, it basically consumes that message, then it consumes this, right? So you have producer here. So this is your topic, which is holding your messages, which is holding your data, right? So these are topics, right? So as I said, that producers will write messages into topic, and then consumers will read from your topic, right? Now, important thing to understand here is how this topic works, right? What is the internals of it? And if you see, I have said that. So you see, I've written that each topic is subdivided into multiple partitions across multiple brokers. So this is something that you won't understand, right, at the beginning of this lecture, but we will understand what is it, right? And then each partition has ordered messages with a sequence number assigned to it, which is known as offset, right? So let's go back and understand. So let's say, as I said, that you have your topic here, right? And then mark it as 0, 1, 2, 3, 4, and 5, and 6, right? Now you have a topic. Let's say you have your order service here. Okay, you have your order service here, and then you have your, let's say, invoice service here, right? So what invoice service is acting as a producer, and order service is acting as a consumer, right? Now in this scenario, you see what will happen. Now think from the problem perspective, that I've said that so let's say the name of this particular topic is, let's say, order events, right? So every time an invoice is being generated, invoice is creating an event and then sending it to this particular topic, right? So this is our topic, and the name of this topic is your order event. So order wants to consume the event, and it will consume it from the order event. So order will know, okay, this is a new order, I will have to process all. So now the problem that could be here is, let's say, as I said, that Kafka maintains the property of durability, the property of performance, property of scalability, right? So the way it achieves that from the perspective of topics is it subdivided the topic into multiple partitions, right? So from the logical perspective, see that if you have order events, right? So you see, you are dividing, for say order event is, there is one partition, let's say partition 1, and then you have partition 2, and then you have partition 3. So you have 3 partitions, 3 different boxes to store your data, right? And then this is nothing but, again, same working as a queue, right? When somebody pushes that message, right? So maybe that message goes to P1, right? And the next time you push it, that message goes to P2, right? Now the message you are pushing M1, M2 here will also get replicated to your P2, will also get replicated to your P3, right? The same message. So it will also have the same message, 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 right? But write will only happen at this P1 partition, right? So let's say here invoice services sends an event of order, right? So that order will go to your partition 1. Let's say it sent partition 3, M3, right? Now M3 will also get replicated to P2 and P3. How it got replicated, and then it basically got replicated in sync manner or async manner, that we will see, right? But the fact is, this same message is replicated M3 here and here. So your order event, whatever you are writing, is being stored at 3 different places. Why? Let's say let's say for some reason you have your multiple consumers, right? So to make it enhance, your consumers can read from any of the partition. First point. Second point, for some reason, if this partition stopped working, let's say this partition stopped working, then you can still read from here to here. For some reason, if this partition stopped working, then you can still keep on writing on this partition and then this partition, right? So the point is, your topic is divided into your separate subdivisions. Those divisions are known as partitions. Why you do it? If somebody asks you, the answer is that's how Kafka achieves durability, performance, scalability, also the high availability from in terms of topics, in terms of storing your messages, persisting your messages, right? So now after this, if you see, I have written each partition has order messages with a sequence number assigned to it, right? So whatever I have written here, right here. So let's understand in the organized way in the article newsletter. So you see, I have created this diagram. So let's say this is our partition 1, and then this is our partition 2, and this is partition 3, right? And this is topic. Now this is our invoice service, which is nothing but your producer, right? So the producer, let's say, will be writing on P1. Let's assume for a moment that your P1 is your leader, right? So from leader, the same message will got replicated to partition 2 and partition 3, right? So you have the same copy of message and partition 3. And then we will see why it basically replicated to three different partitions. So there will be some replication factor and all those things will come up. We will see later in the later part of this lecture, right? Now let's say your producer is writing on partition 1. Assume partition 1 as a leader, current leader. Same message you have partition 2, same message you have partition 3. Now from the consumer perspective, now you have order event. Now that order event service is running in 3 instances. You have 3 instances. You want to scale horizontally, scale your order event. Now there could be chances that if your order event service 1 of order is maybe lagging behind in terms of order event. So maybe, for example, it's still want to process the old order because the current offset is basically 2. So that basically defines at which index this particular consumer wants to read the data from the partition, right? So if it is offset 8, that means it will read from the index 8, right? So offset defines the sequence number from where you want to pick your message from the partition. Now another fact is the ordering of message can only be achieved within single partition. You cannot achieve ordering of events within multiple partitions, right? Because you see, each partition is persisting data. So there is no way that you can maintain a sequence within multiple partitions. So ordered partition will contain ordered messages. That also means that this is in sequence, right? Within a single partition only. All right. So this is the concept of offset. Consumers can read particular message using offset, right? Now these messages will remain, because how durability, I say message will be there in your Kafka, it won't go away till a period of time. That period of time will be known as a retention period, right? So that message will be retained for a particular retention period that you will have to configure, right, as part of your cluster. So those are the basics of your topic, right? So now let's move on and understand your Kafka internal architecture, right? Now, in case you think that, okay, I want to learn more about Kafka and streaming and all those things, creating a data platform, you can comment it down. Just comment it on yes or no. I'll come up with the next video, right? So now let's talk about the Kafka internal architecture, right? So when I start Kafka internal architecture, first time, even if you remember, right, in the beginning of lecture, I said brokers. So brokers has nothing. So let's say you want to run your Kafka, right? Now remember that all those queues and topics, everything, who will maintain this, right? So Kafka will also be a service, right? So your Kafka will also be a service. So now remember how Kafka will work. So Kafka will also work as a service, right? So it's also server. You can also call it node. So this particular guy is also known as your brokers. This guy is known as broker. Nothing but a server that is running your Kafka service, right? So assume that is known as a broker, right? In terms of messaging platforms, architectures, these services are known as brokers. I have said a server node that handles all operation, right? Because this particular node, this particular guy will handle everything, right? All the read operations and all the write operations, right? Okay. Now, what is Kafka cluster? So the way you run your Kafka, the way Kafka gets deployed is in form of cluster. So clustering is nothing, right? So clustering is very simple concept. If I ask you, if you basically run 3 servers working together in a way, so it acts as a single unit of work, right? So this is nothing but your cluster. So you have server 1, server 2, server 3, right? So all these Kafka servers are running within a single cluster, and you call it as cluster because you have, what you've done is you have done clustering, right? So you've combined them working as a single unit. So all these servers, now let's start calling these servers as a broker. So it will broker 1, broker 2, broker 3. So how could I say that this is your Kafka cluster has broker 1, broker 2, broker 3. So the cluster of 3 brokers, right? So as I said, group of brokers, messages are stored among brokers in the round robin fashion. Producers can select partition to send messages. So now if you have producer here, your producer wants to send a message, right? Now how can it send a message? So the basic way of distributing the load is you're doing a round robin, right? So one call to here, one call to here, one call to here. So from the 3 call, every partition will receive 1/3 of call, right? So this is a round robin fashion. So each partition, so this producer can select a particular broker as well to your send the data, right? Writing the messages. So leader node, as I said, that within the partitions there will be one leader which will handle all the write operation, right? And then other followers, so it's a leader follower basically concept. So let's say if you have this node, this node, this node, and this node, so this is your leader and this is your follower 1, this is your follower 2, this is your follower 3. If you remember, if you go back to my system design series, right, there is a lecture on I think a leader follower right replication. You can go and refer that. That's a single master write replication. I think that is the title of video. So the way it works is whoever wants to write will always write to your leader node, and then the responsibility of leader node is to send that the same data to your follower nodes, right? If somebody wants to read, that guy can read from your leader node, from your any of the follower nodes. So this read operation can be done from anyone, right? So that's how you are scaling your read, and then you are basically making sure that your write operations only happens at one place, so there will be no conflict of the conflict of data among other nodes, right? So this is leader follower. So as I said, if you go here, as I said when I was talking to this drawing, I said that this P1 is acting as a leader. That means partition 1 is handling all your write operations, right? So that is the concept. I told you the concept of followers as well. Follower will have the same data whatever your leader has, and then that's how your Kafka maintains the fault tolerant capability. Because if you remember when we were talking about this, I said, let's say if this partition goes down, your consumers can still read from here and here. What happens if your partition this guy goes down, the leader goes down, one of the follower will become a leader, right? So that's, you are tolerating the fault. You are basically you are opposing the failures in the system, right? That is the fault tolerance capacity. ZooKeeper is basically nothing but a coordination system. So if you have multiple nodes running here, how these nodes will be talking to each other, right? There have to be some coordination system in place that will take care of each other. That is why when you deploy a Kafka cluster, before that you need a ZooKeeper, right? So when you deploy ZooKeeper, and over to that you deploy a Kafka cluster. So that's how your nodes talks to each other, right? That is why you need ZooKeeper. So whenever you want to install the Kafka in your local system or server or wherever XYZ, you will have to deploy a ZooKeeper as well, because it's a coordination system. It makes the nodes within cluster to talk to each other and work properly. Then you have the replication factor. It's very important, right? Replication factor, let's say for a topic, if you have replication factor is equal to 2, right? So what it means, it defines the total number of replicas for the topic, and then replication factor value 1 are not replicated. So that means, let's say, as I said, for a topic, if you have, let's say you have a cluster of partition 3, right? So you have partition 1, then you have your partition 2, then you have your partition 3. Now if you have replication factor for order events, right, let's say you have replication factor is equal to 2. What it means is the same data when you are writing on P1. So let's say P1 is a leader, right? When you are writing an operation, let's say M1 here, so you are writing M1 here. So replication factor, a cluster will see that I will have to replicate, leader node will see that I will have to replicate M1 to a different node as well. So it may write the same data, right, to maybe partition 3. So that is the replication factor. So to how many total number of copy of the same message will exist, will get persist in the different partitions, is something which is defined by a replication factor, right? So how many replication will you have is something which is defined by a replication factor. Very simple. So this is a topic level property, right? Then you have n-sync replica. It's very interesting. Now try to understand this, right? In-sync replicas, let's say in-sync replicas, right? In-sync replicas. Now let's say you have your partition P1, right? You have your partition P2, you have your partition P3, right? So partition P1 is your leader node, and then these are your follower nodes, right? Let's say let me write follower nodes. Let me write follower node. Okay. Now producer, let's say producer wants to produce a message. So it will, what it does is it will write a message to your partition 1 since it's acting as a leader. So this message basically is been written to P1. Now let's say for this particular topic I have the minimum ISR, which is n-sync replica. For example, let's say I have for this particular topic, I will write here for the order events, I have RF is equal to 3, means replication is equal to 3, right? And then I have minimum ISR is equal to 2, right? So what it means, let's try to understand. It's very important. Now when somebody will write a message to P1, because P1 is a leader, right, it will see that your minimum in-sync replica is 2. So if you write only in P1, your write will not be considered as successful write. Why? Because you have minimum in-sync replicas is equal to 2. That means the same write needs to be updated as part of the write operation, needs to be updated or replicated, let's say M1 here, then only your write operation will become successful, right? So that's the concept. If you have minimum ISR is equal to 3, then your write operation will only be considered successful once your write is basically replicated at the same time as part of your write to all the 3 partitions, right? This is your minimum in-sync replica. Now let's say if you have ISR is equal to 2 and RF replication factor is equal to 3, then what will happen? Producer will write to your M1 at the same write operation as part of M1 will also get written to partition 2, right? Because ISR is 2, and then written operation will get successful, right? It will get acknowledged. So both node will acknowledge, okay, that the write operation is successful on the both sides, then write operation will be considered at the successful. Now later, maybe as part of the passive replication, the same M1 will also get replicated to partition 3 because of the fact you have replication factor is equal to 3, right? So that's the concept of replication factor and your in-sync replicas, right? I have basically whatever I have explained I have written here, right? That replica is the same as leader has. A leader goes on one of the node as will be acted as leader. The Kafka 0. So this statement says basically I told you that already. That's how Kafka makes the system fault tolerant. Let's say if from one of the node, if one of the node goes down, from the multiple of node, one of the node goes down, leader goes down, then the other node will start acting as a leader. So that's how your system, you never, write operation will never get stop, right? So that's a zero data loss condition. Okay, and then you have the concept of consumer group. So consumer group, let's say you have your 3 partition, right? Partition 2, partition 3, partition 1. So this guy is your leader. Now you have a consumer A, let's say consumer A, and then you have your consumer B, right? You have 2 services running. Now somebody writes the copy of M1, it gets returned here, it gets, let's say, replicated, get here. This guy receives a copy of M1. This is a consumer service, order consumer service, and this is also order consumer. Now there may be chance that the same message will also be consumed here as well, right? So that's such you are consuming the same message twice. There is no point here, right? You will have the business issues. You will start having the business issues or the logical issues as well. So the correct way of doing this is Kafka says what you could do, although you could have the multiple instances of consumer, but you define the consumer group, right, to both of the instances. So this guy and this guy will have the same consumer group. So Kafka will ensure this copy of message is only be delivered to one of the instances services in a consumer group. So there could be chance that this guy receives the message or this guy receives the message, but the message will only be sent once to one of the consumer in a consumer group, right? So that is the concept of a consumer group, right? So if you look at this diagram, right, so we have this broker, the Kafka cluster, and you have this Kafka cluster, and then they are different brokers, right? On each broker has multiple partitions. So let's say if you've configured your cluster to have 3 partitions, so your 3 brokers will have 3 partitions, right? So these are the partitions will have the same data. That is why I kept the same color, right? So now let's assume a scenario where you have the replication factor is equal to 2 and minimum in sync replica is equal to 2. Now, or assume for a moment that you have replication factor is equal to 3 and minimum in sync replica is equal to 1, right? Now what will happen in this case if some producer writes a message to, let's say, broker 1, partition 2. So consider partition 2 is acting as your leader. So now that particular message will be returned to broker 1, partition 2, which is your leader. Then as part of the replication factor is equal to 2, then the write operation will be marked as successful operation. Why? Because you only have minimum in sync replicas is equal to 1. Assume it as 1, although I have returned 2. But later after some time the same message will get replicated to the partition, the broker 2 or broker 3 accordingly, because you have the replication factor value is equal to 2. So the message will be kept at, the replication factor will be 2, message will be kept at 2 different places, right? So that's how, this is how I have defined your order events, right? And this is what I have said here. So let's say if you have your in-sync replicas is equal to 2 and replication factor is equal to 3. Now what will happen? Producer will write it to partition 2 since it's a leader. As part of the same write operation, the message will be returned to your broker 2 because you have minimum in-sync replicas is equal to 2, right? Now write operation will only be considered as successful once the broker 1 and broker 2, all these partitions, sends the acknowledgement that the write has been persisted successfully. So write operation will be considered successfully to producer 1, and then later after some times if you have the replication factor is equal to 3, although I have written 2, will the same message, the same copy of message will be replicated to broker 3 somewhere here. So you will have the replication at 3 different places, but the write operation, the in-sync replicas was 2, so the write operation happened considered successfully only after the replication, the 2 replicas was in sync as part of that write operation, right? Same thing I have written here. You can go over to this newsletter, and you can subscribe to suchit.substack.com. There I'm writing all the newsletters. The same newsletter, you can find it there itself. If you really like my content, then you can follow me on LinkedIn, and then this is my GitHub repository. You can go and check it out. So in the next video, I understand from some of you, you may have understand the Kafka, but you may not be able to visualize it. In the next video, I'll run a Kafka cluster for you, try to send some message, consume it, so you'll get an idea. That is how a Kafka works. Okay. And also sometime back, 1 or 2 days back, I created an OAuth2 video. So I started getting some queries that, because that was a conceptual video, I will be creating another video where we will use some kind of authorization server and generating access token, refresh token, play around it, will understand. So you guys will have an idea, start to visualize how these works basically. So when you can connect the concept part to the theory part to the practical part. Alright, so far we have understood the Kafka architecture. In the next video I'll come up with the practical part of it. Till then, thank you so much guys.